Okay. So what I'll do is I'll just go through because this is the one that was already open, that I had open. I'll go through the majority of the problems that are applicable for this online class, um, because some of the questions in here are blended with my face-to-face class, um, and some of the questions are non-applicable. So I'll go through that along with the other document that is right below it. This one's the one that is a little bit more applicable. So I'll go over that after so that you are prepared. And then come next, well, that's in 2 weeks. So on December 2nd, you guys are going to be taking the final exam, um, right here, via this link. So there'll probably be, I think that's about 23 questions. You'll have to click on it. Right now, you should be able to see it, but you won't be able to access anything in there just yet. Um, Let me see if I can try it. We have you as a student, just like you guys are. So right now, you'll see that grayed out. So what you're going to need, if you don't already have it, I think I said this before in the past, you're going to need to have your ID. Make sure you can find a quiet, isolated room. For example, maybe a library that you can um, rent out, or you utilize the room for a couple hours. I would say uh, at a probably at a maximum 2 hours. I would guess that on average the test would take somewhere between an hour, hour and a half, but I would give myself an extra half hour so you can check, or in case something goes a little haywire. Um, so make sure you have all those things along with your web camera. I don't have a visual on you, so if you have any questions, you can, I think you can raise your hand using the button or unmute your mic. Are there any questions at this point?
Does it
Okay.
have to be your student ID?
Uh, no, it just has to be a picture ID. Okay. Any other questions? All right. So as it relates to your final grade, your final grades will be posted that last Friday of um, of the year. I believe that is somewhere around the 12th. Um, don't quote me on that yet. My days are starting to bunch together here. Let's look here. So for you guys, yeah. So the 12th would be that last day, and that will be the day that I have them in. So if you have any questions as it relates to um, your grade, it's going to be really important that you ask me, um, obviously prior to the lab final. So this will be the ideal day or the ideal week to get your appointments in. Some of you guys have already scheduled appointments. We've talked a little bit. Um, so get those questions in, because this week of the 8th, I'm in really busy mode here, trying to get grades together. Likewise, in this week when I come back from Thanksgiving break. So I would strongly encourage you guys, if you have a question as it relates to your grades, um, get those questions answered. Now, I am still working on some of your labs. Some of you guys may see that the grades are trickling in, um, slowly but surely. I usually run at least 2 weeks behind in getting those back to you. So your patience is appreciated. Um, we've been off for a little bit, and I think you guys only had one assignment that was a group assignment, this RLC circuit that was due. I think I had you turn it in on the 12th. So we should be good there. And I think I'm working on your um, think I'm working on your RC circuits right now, so I'm not too far behind. But again, patience uh, and um, check your grades to make sure that everything lines up. Every once in a while, what may happen is in the grade book, I may have set up the grade as an individual assignment, and every once in a while, it'll show up with that one person getting the grade. But for group assignments, everybody gets the same grades. So I'm on that. No need to worry about that. I can easily see that and I'll have that corrected. So don't worry too much about that. Now, if you didn't participate in a particular assignment with your group, I think you know what the outcome of that is. I do drop one lab um, lab report. So of those 9 lab reports, I'm going to grade 8 of them. 80% of your grade comes from that, and the other 20% comes from the final exam. Okay. Questions? All right. So let me get started on the first lab review that I put out there. Okay. Don't mind. I'm going to put you guys just on a brief hold because I really want to have this on my iPad so that I can write a little bit more rapidly. So uh, stop sharing here real quick. All right, here we go. So let's talk about number one. It says, how is an ammeter connected when placed in a circuit? So what we'll do here is let's remember what an ammeter is going to look like. We typically are going to have a little A circuit here. And let's just say that we had a resistor in the circuit coupled with a battery. So anytime we place an ammeter in a circuit, it is always in series with the circuit, as opposed to a voltmeter. A voltmeter attaches parallel. And remember what you guys had. What you guys had was you guys had the object that looked like 2 little prongs called a voltmeter, and you were able to attach it at various points along the circuit, and they were always placed in parallel. When you had the ammeter looked like in the schematic, it looked like a little box here, and it had the current reading in here, so you can see how many amps were going through it. So make sure you understand the difference between those two. All right, number two, it says that we have a 4,000 ohm resistor and it's connected across a 220 volt battery. These are the only 2 components, it's a misprint, in the circuit. What current will flow? So that resistor, you should know the schematics of a resistor. You have a battery. Those are the only 2 components. And the resistor is of 4,000 ohms. The battery is 220 volts. We want to know the current. So current is based off of Ohm's law. In this case, the current is going to be the voltage divided by the resistance. And we would simply take the 220 volts and divide it by the 4,000 ohms, and we would get something in terms of amps. So we should realize first off that this could not be the right answer. And Just gonna plug this into my calculator instead of looking at the answers at the end and make sure I can get a nice answer. Should be the 0.055. So 220 divided by 4,000 is the 0.055 amps. Okay. So what you should realize here is that units of current are going to be in amps. Those are the units. Obviously, volts. Voltage is in volts, and resistance are in ohms. So that's probably the best takeaways from that. Number 3. And let's make this so we have a little bit of room. So what I'm going to do is I'm going to duplicate this page here. And block out some stuff here so it'll look a little cleaner for us. Okay, so we have 4 equal resistors connected in series, and they have the same current and the same voltage. So this is a true or false statement. So let's see. We have these 4 resistors. So we have resistor resistor 1, resistor 2, resistor 3, and resistor 4. They're all connected in series, and they have the same current going through them. So if each one of these have a current, let's just call it I1, and the voltage across here, let's just say is 10 volts, would they have the same voltage across each resistor? Well, so across each resistor, there would have to be, if these are the only components in the circuit, they would all have to be the same because, let's see, if the resistance were all the same as well, so we have equal resistors and same current, so therefore the voltage drop across each one of them, VR, has to equal, have to all be equal. So that would be a true statement. Okay, let's look at problem number 4. Number 4 down here. Number 4, we have a 4 ohm resistor, and it's connected to a 12 ohm resistor, and this combination is an ideal DC power supply with some voltage V as shown. If the total current in this circuit is 2 amps, what is the value of voltage of the voltage? Okay. So in other words, what we're trying to do is we're trying to figure out how many volts are running through the battery right here. So the first thing you want to do in a situation like this is you want to recreate this set of resistors, and because they aren't being supplied the same current because there's a node here and the current splits off. In other words, this resistor is grabbing more current than this resistor. So we should know what a set of resistors in parallel look like. We're going to need to kind of condense this down into a single resistor. So let's redraw this. And this is going to be my goal here. That's a resistor. Sorry, it's a little messy. There's our voltage V. And remember what we have over here is we had 2 amps going through the setup, through the node. So when we have resistors in parallel, we use the equation 1 over R1 plus 1 over R2 is going to equal to 1 over the equivalent resistor. And this is going to be my equivalent resistor. So we're condensing these two resistors so that they look like REQ. So let's do the math here. So 1 over 4 plus 1 over 12 is equal to 1 over REQ. So if I change that, that would be 3 12s. So we have that the left side is equal to 4 12s, which implies that by flipping both sides, instead of 1/3 right here, we would get 3 over 1 or 3 ohms. So REQ is equal to 3 ohms. Well, remember what our goal here was. Our goal is to figure out what the voltage is in this case. And now we're back to using Ohm's law. So Ohm's law tells us that the voltage is going to equal to whatever the current is that's being pushed through, which was the 2 amps, multiplied by the equivalent resistance, which is 3 ohms. And so there should be 6 volts being pushed out of that that battery. Okay. All right, next problem. Number 5. Kind of similar, but this time we have resistors in parallel and resistors in series. So we're going to need to kind of condense this quite a bit. So let's let me paste up this little block here so we can work off of it. I'll do a little bit of work off to the side here because I think most of you guys will probably understand how to get equivalent resistors that are in series. So those two combine up to make a 4 ohm resistor. So there's a 4 ohm resistor. And down here, we're going to make another 4 ohm resistor. And so our first setup is going to look like a 4 ohm resistor here, a 2 ohm resistor here, and another 4 ohm resistor here. So we just simply combined the top two resistors into the schematic that I have here. So let's label those. So we have 4 ohms, we have 2 ohms. I won't put the units in there. We have another 4 ohms. Now these three are in parallel with one another. And what our goal, again, now at this stage, is to make one big resistor from those three, and we'll call that REQ. And I think we probably got, yeah, we'll call it REQ. We don't need to give it any special name, 1 or 2. All right. So same formula that we had a minute ago. So 1/4 plus 1/2 plus 1/4 is equal to 1 over the equivalent resistor. In this case, let's see, the common denominator here is 4, so that becomes 2/4. So we have 2/4, 4/4. So this is just equal to 1, which is great because when we flip it, we still get 1. So this resistor over here is 1 ohm. Okay, so those 5 resistors give create one big resistor. We're thinking of it as one big resistor of 1 ohm. Okay, and that's all we were asked to do here. So our answer here should be C. And let me copy this page over again so we can do it again. That other stuff here. And let's answer. We'll answer number 6 and number 7 on the fly here. So number 6, it says state Kirchhoff's junction rule. So the junction rule means that at a node, in other words, where we have a split of current, it implies that the current in is equal to the current out. So, in other words, if I have some current coming in to this junction, let's just call it I1, that amount, if it's going out, I2 and I3 should sum up to it. Okay, so it's a pretty simple concept. It's just like water. If you have 5 gallons, let's use my laser pen. If we have 5 gallons of water coming in to this junction, and just making up a number here, 2 gallons come out here, 3 gallons need to come out over here. Okay, so same current in, same current out, same total. Okay, and we're going to use that in just a second. The second thing says about Kirchhoff's loop rule states that the sum of all voltages in a loop, let's just put L1 here, and L1 might be this loop here that goes in this manner. Is going to equal 0. Okay, so let's just say that we're going, and we're going to look at this circuit here in just a second. Let's just say that I decided to go in this direction around this part of the loop. After figuring out all my voltage drops, if I started here, let's put a red dot here. If I start here, pick whatever you want, place to start. and I decided to go in this manner around this loop, it's just completely arbitrary which direction I choose or you choose. After I figure out my voltage drops across each one of these components, it's going to add up to 0. Okay. So that's what we're going to really need to focus on for this next problem here. And that's what Kirchhoff's loop rule is. It could be also, you could also look at the total loop in this outer circuit component as well. You can look at this inner loop right in here, and you can pick whichever direction you want, clockwise or counterclockwise. When you would travel in this inner loop here, you might decide, decide it this way, that this direction might be your loop of choice, and make sure you figure out where your starting point is. Let's just say I started here. Where you start is completely arbitrary as well. We should get that the voltage drop across each one of those sum is equal to 0 after we sum them all up. Okay. So let's look at that. So while I'm going through that, does anybody have any questions? All right. So I've duplicated that. Let's erase all of this. I need a little bit of room for this problem. Let me get here. Okay, so for problem number 8, we got a pretty complex circuit here, and our goal is, let's see, in this figure we have currents I1 and I2. So I1, I2, and they're 0.13 and 2.22 amps respectively. So let's just write that off to the side because we're going to probably need that. So I1 is equal to 0.13 amps, and I2 is equal to 2.22 amps. And we're going to want to know what the potential difference, in other words, the voltage drop from A to B is. In other words, as we go from this point to this point right here, we want to know how many volts, what the difference in the voltage is. So you'll hear potential difference. You might hear that as well. All right. So in this case, this is a case where Kirchhoff's law is going to come into effect. So let's set up a couple different pieces here. So first thing we're going to want to do is we're going to look at the current rule, Kirchhoff's junction rule or current rule. And I'm going to use point A as a starting point. And I'm going to go to this node right here. So Kirchhoff's current rule just basically again says we look at a node, that's where the current splits off, and we want to determine what the current in and the current out are. So let's just call the current coming in here, we'll call that I1. Right, so we'll just assume that the current is coming in this direction, and it may not be. So if it's not, we can make that correction. And let's just say that in this direction, we have I2. And in the other direction, we have I3. Now, you can make the same argument over in this area as well, but for sake of time, you'll notice that when you replicate the two junction rules, the equations are basically identical to one another, just plus a minus sign, or they only differ by a minus sign. Okay, so we're only going to set up one equation here. So with regard to the current, and we'll start at that first current, I1, which is going to be positive because we're assuming that it's going in, minus I2, minus I3. Essentially, the left side is equal to the right side, or they cancel out and they make 0. Okay, so that's going to be our first equation that we're going to build off of. The second rule comes from our loop rule, and this is where it gets a little bit shaky here, so we got to be really cautious. So I'm going to design my loop, and it's completely arbitrary how you design it. I'm going to make my loop go clockwise. So this is going to be L1. And so my L1, I'll write over here because I'm going to need more room in just a second. So my L1, we're going to see all the voltage drops across this loop. Okay. Now, when I go across a resistor in the direction of the current, there's going to be a voltage drop. So as I go across this first resistor, I should have a voltage drop of, let's see here, my voltage drop is going to be minus, and how much? It's going to be the current. Well, we don't know. Well, we do know the current. I'm just going to put I1 for right now, times the resistance, which is 10. Right? That's Ohm's law, current times resistance. So there's our first drop in that loop. And then now we come through the loop. So we've come through this, and now we're going through the node, and we're going across this next component, which is the battery. And it's telling us that the battery is 3 volts. Let's just put an arrow here so we know. And you can see based on the polarity, let's highlight. So this is 3 volts here. And you can tell based on the polarity, as it goes from negative to positive, there's going to be a voltage increase. So batteries are fairly easy to look at and determine if there's a voltage drop and a voltage increase. So pay attention to the direction of your current. Your current is traveling in this direction here. So therefore, there should be an increase of the voltage, in this case of 3 volts. So we don't need an Ohm's law factor in here. So there's going to be an increase of 3 volts. Remember, all of these are voltages. So we've gone through the first 2 components in loop 1. A resistor of 10 ohms, a battery of 3 volts. Now we're going to go through this next resistor. So its resistance, you can see here, is 3 ohms. And there's going to be a voltage drop. So again, there's always going to be voltage drops in the direction that the current is flowing, or you assumed it to be flowing. And so here I give you, and I'm telling you that the current is flowing in that direction. So here we go again. So it's going to be I2 Let's see, what else? Times the resistance. The resistance is 3 ohms. Okay, so we've gone through that part of the loop. We're going to continue on through this loop. So we're traveling in this direction now. So the last component to go through is this last battery here of 5 volts. And you can see here that there's a voltage increase. So plus 5 volts. And all that is going to equal 0. Okay. We'll clean that up in just a second. Now, you may notice here that I chose my current to be going opposite of what was already given for I3. Well, it's not a big deal. We'll make the correction in just a second. So let's look at a second loop. So this is going to be loop 2. Let's use a different color so we can kind of see that. So loop 2, again, the direction that you want to traverse is completely arbitrary. I just like to go clockwise each time. And I like to start at the top right. It's just my personal preference. You figure out which direction you want to go in, and that'll be fine. So for loop 2, if we start at this point here, and we're assuming that our current is in this direction, as we go through the resistor with the current, the assumed current, we should get a voltage drop. So the voltage drop is going to be predicated on the current, which is going to be I3 times the voltage. And remember that was negative. Okay. We've gone through that first component. Now we're going through this battery here. So through the battery, you can see in this direction that our polarity goes from positive to negative. So there's going to be a voltage drop, in this case of 2 volts. Okay. So we've figured that one out. Now we're coming back through. Bear with me here. I know this is a little bit tedious here. So we're coming back through this this set of components as well. All right. So as we go through this resistor, you'll notice that current flows in this direction. When we go opposite of the current across a resistor, there's going to be a voltage increase. How much? There's a voltage increase there. It's going to be the current using Ohm's law, I2 times the resistance, 3 ohms. Voltage increase, opposite of the direction of the current. And then finally, so we've gone through this resistor for a second time. It's okay. You want to repeat that. And then now finally, we're going to go through this battery again. So look at the polarity there. You can see that it goes from positive to negative. And so we're going to have a voltage drop. How much? You can see that it's 3 volts. Okay. So these are our 3 equations that we're going to be looking at. It's probably a little bit more than what we needed to do, but you're going to probably see some more complex problems than this. So I want you to be prepared. So now we'll have a system of equations. I1 minus, let's do this. I'm just going to copy some of those equations over. So this first equation, put here. So there's our first equation. Our second equation is going to come by way of L1. So up in here, I'm going to clean that up. I like to put like terms underneath or above one another. So let's put this term right here. Let's make that negative 10 I1 minus 3 I2, and then equal to 3 and 5 add up to 8. But when I move it over, we're going to move it over and make negative 8. And that comes by way of L2. Sorry, L1. And then finally, L2. L2, there is no I1 term. I2 term, I'm going to write it up above here, so bear with me. So we have 3 I2s. We have negative 4 I3s. And the constants add up to negative 5 on the left side, so 5 on the right side. Okay. So here's my system, and you should be able to solve this system. You should be able to solve this system for any one of the unknowns. So let's see. A lot of this was already given, so we can fill in some of the blanks. I1 and I2 were given, so we should have 0.13 minus 2.22, and that should equal to I3. When you subtract here, you'll get negative 2.09. And remember, I said not to worry about the direction. This minus sign tells us that we need to change the direction of what we assumed it to be. So I3, if we were to make a correction, points in the opposite direction. So change direction in your final drawing. Okay. And it was as what was given. Okay. So I3 is that. We know I2. So I think we should be good. So now if we're trying to figure out the the voltage drop from A to B, traveling in this pattern here, we should be able to figure that out. Let's do it off to the side over here. Okay, so on the left side over here, the voltage drop. So it would be the where's my pen? It would be the 10 ohms times the current, which is 0.13. There's a voltage drop there. Let's put a negative sign in here. Yeah, put a negative sign in there. And then following this path right in here, we're going to see a voltage drop, a voltage increase. So +3 over there. And so let's see what I get when I do the math here. So that would be negative 1.3 plus 3 And so, what's that? 1.7. Okay. So there should be a difference of 1.7 volts as we go from this point to this point right here, from A to B. Okay. Now I did a lot more than what was necessary for this problem. I probably could have went right into that step, but I wanted to show you how to solve a system using Kirchhoff's law, similar to what you had in your lab work. Okay. Are there any questions there? Questions? All right. Let's see. Number 10 looks to be overlapped. So let's duplicate that page one more time. And I'm gonna get rid of that. All right, so number 10. It says that we have an 8 microfarad capacitor, and it's connected in series with a 10 kilo ohm resistor. And we want to try and figure out the time constant, essentially, from this circuit. And it's also connected to a 20 volts DC power source. So let's see what we have. Oh, and by the way, you know, I sometimes forget um, my different units as well. So I understand. So what you can do is you can have a 3" by 5" note card. You're going to need to show it to the camera. So make sure you have that up and available. Okay, hold on one second. Can somebody unmute their mics and let me know if you can hear me?
Oh, I hear
I
you.
can hear you.
Thank you. All right. So in this case, we have our goal here is to figure out what the time constant is. So our time constant is T, and how we calculate this time constant and what the time constant is depending on if you're charging or discharging a capacitor. It's either going to ramp up in this fashion or it's going to ramp down and discharge in this fashion, right? And it does something really special at each one of these points. Usually after one tau of charging, it's charged up to about 63% of the max capacitance. So it ramps up very fairly rapidly, depending on what your time constant is. And it does that for all capacitors, which is pretty cool, right? So the resistance would be the 6 times 10 to the third ohms. We won't put the units in here. And the capacitance is the 8 times 10 to the -6 farads. Okay. So in this case, let's see, we multiply those two, we get 48. Multiply those two, we get 10 to the -3rd. And so we get, what's that, 48, so 0.048. And these are in seconds. Okay. So notice here in the answer, it's given us in milliseconds. So milli means 1/1000th. So let's see how many milliseconds. If you forget how to convert, just again, write out what you need on your note card. So there are 1,000 milliseconds in 1 second. And so seconds are going to cancel each other out. So in this case, we can see that by moving the decimal back over 3 places to the right, we get 48 milliseconds. Okay. Questions on that? Okay. So a couple things that you need to know also in terms of voltage increases and voltage decreases. These RC circuits are going to charge and they're going to follow this pattern. Okay. So what does this mean? This means that your voltage as a function of time, if I wanted to, I could write V as a function of time, means the same thing, is going to charge at a rate such that this number right here is typically your max voltage output. In other words, if you have a battery and you have a resistor and you have a capacitor, that's a bad picture. Battery, resistor, capacitor, you have this type of setup, and your power source, your battery, let's just say you have a 9-volt battery, this is going to be basically the max voltage that it's going to charge up to. And it's going to look something like this one up here, sort of exponential in shape. And after 1 tau, in this case, the tau value is 48 milliseconds, so pretty rapidly. So after 48 milliseconds, it's going to be at 63% of your max voltage. Okay. If you're discharging, it's going to follow a pattern kind of similar to it. It's going to look like this. V naught 1 minus e to the minus t over tau. And it does something, again, very similarly, but after 1 tau, it's going to discharge to, I believe the number is about 37%. So right about here, after 1 tau, whatever that value is, I don't want to put 48 milliseconds, but if it was 48 milliseconds, it would be at 37% of V naught. Okay. Just duplicate this page again and then delete all this stuff here. Too much. Again, duplicate this page. Delete. I'm going to erase all this in here. Get back to what we're looking at. I know there's a faster way of deleting all this stuff, but I kind of like doing this with my stylus. My son says it's satisfying. All right, there we go. Okay, so we just did number 10, number 11. In order, and we did this earlier, in order for a voltmeter to measure a voltage, it must be connected in parallel, right? In parallel. So one more time, let's just say you were trying to measure the voltage across a resistor, the voltage drop. on your in your schematic, you had this item. It looked like two little probes, and you put the probe on one side and you attach it to the other side, and it showed you how many voltage drop. Okay, and this is in parallel, as opposed to the ammeter. One more time, the ammeter is in series. Okay. All right, number 12. Below we have a graph that represents current versus, or voltage versus current. What are you able to determine given Ohm's law about a circuit? So it reads that Y is equal to, can't read that, 3.11x minus 0.24. So what you should be able to discern here is that this looks like a it looks like a line. So you should discern that it is a line, and it has a slope. I won't use M. So the slope based on this line format is 3.11. And how is the slope determined? The slope is determined by taking a ratio of rise, in this case voltage, over run, which is the current. And then for our purposes, that's a modification. That's just Ohm's law. And so that is equal to some resistance. So resistance values are given in ohms. So this would be 3.11 ohms. Okay. Don't worry about number 13. That's more applicable for my my face-to-face class. So we can bypass that one. All right, 14. So number 14, we have two resistors, and they're going to be connected in parallel. And this combination is connected in series with 3 ohms. What is the equivalent resistance of this system? So let's see what we have here. So we have two 4-ohm resistors connected in parallel. So two 4-ohm resistors connected in parallel. This combination is connected in series with a 3-ohm resistor. Okay, and let's assume that those are the only components in a circuit. What is the equivalent resistance? So we kind of did this one in the previous problem. We'll do it one more time. These are 4 ohms. I won't put the units in here for the sake of time. This is 3 ohms. These two 4-ohm resistors. So typically, you guys, most students don't have a problem with these. It's just a matter of which one do I do first. I would say always do the most complex part first, and typically those are the resistors that are in parallel with one another. So these two resistors that are in parallel, let's see, 1 over 4 plus 1 over 4 is going to equal to 1 over, we'll call it REQ1 because that's just a preliminary stop for us. We're going to erase that. Let's see, we get 2/8. Sorry, we get 1/2 on the left side. So 1/2 is equal to 1 over REQ 1. And so REQ 1 is equal to 2 ohms. So for sake of space here, let's just erase this. And that now gets replaced with a 2 ohm resistor. And we're off and running. This is pretty straightforward. Resistors that are in series just simply get added together, and we just create this new resistor that is of 5 ohms. So just redrawing, we just get this 5 ohm resistor. Okay. So duplicating the page one more time here, class. Bear with me. So this. Okay, so let's look at number 15. Number 15, we have a spherical concave mirror, and it has a radius of curvature R. And we want to try and determine the focal length. So if you remember, we had to draw ray diagrams. And so in this case, for number 15, I'll just draw it right on top here. The mirror looked like this. We had some axis point here, and our radius for this circle was R. We can measure also R along this length here, but the focus was halfway in between. So the focal length is just half of R, okay? So if I give you a ray diagram, or if I give you a concave mirror, and I put the, let's just say I put the center at 8 millimeters, you should know that the focus is going to be at 4 millimeters, and vice versa, okay? Number 16. Single concave mirrors produce images that are, let's see. Well, this one's going to vary because it depends on where we put the object. And so what I'm going to have you guys do, and you're going to need to make sure you have this proper as well, is you're going to need to have, hope everybody's listening, make sure to bring a straight edge. And that straight edge could be your stylus, pencil, something that you can draw a straight line. Because what's going to happen is, let's just say I put an object at a specific point. I'll put it over here. You're going to need to draw ray diagrams. And if you remember how we did it, we would parallel, focus, and then we went focus, parallel. But in this case, we couldn't get an object. So you should know how to draw, and it won't be one of the complex ones. So you should know how to draw the image from a mirror. So a better example would be And this is not drawn to scale, so it may not come out properly for us. So let's just say I put the image right here. So here's the image, and then I draw my rays. So I go parallel F, and my next line should be F parallel. Okay. So my image is going to be where the lines intersect. So they're going to intersect right down in here. Okay. That second intersection is what we're looking at. Okay. So make sure you're able to draw the image. The image. Okay. Number 18. Number 18 says that a laser beam strikes a plane's reflecting surface with an angle of incidence of 43 degrees. What is the angle between the angle of incidence and the reflected ray? So one more time, again, very similar. Let's just say that here is the surface, and anytime we have an image, a light ray, it's going to hit the image or the surface. Let's just say that here's my light ray coming in this direction. Give it an arrow so you can see it, which direction. It should hit this surface such that it is normal to that line. Okay, it's going to reflect off in this direction as well. And the angle of incidence, that angle there, call it theta I, should always be equal to this reflection angle. Okay? So you always look relative to the normal in terms of what angle we're looking for. So if I ask you which angle, well, it could be, it could be this angle here, but no, relative to the normal means you draw a normal line. That means a line that runs into the surface at 90 degrees, right? So you do the best you can. It runs into it at 90 degrees. In this, let's say we had a light ray coming in this direction, and then another one coming in this direction. The angle that I'm looking for is relative to the normal. So it's always between the light ray of reflection or incidence and that normal line. Okay. So you always choose that angle right in there. There's theta of I. That's the incidence angle. And it's always going to bounce back at the same angle. Okay. Number 19. To find the image of a ray by ray tracing requires a minimum of 2 rays. Okay. And that's the concept that we talked about of being parallel, going parallel, and then through the focus, and through the focus, and then parallel. And I think I put a video on how to draw ray diagrams. So the last, or 20 and 21, I'm not going to do, but you should practice this by drawing, um, drawing, let's see, maybe I'm thinking of something else. Okay, so number 20. An object is 12 centimeters in front of a concave mirror, and the image is 3 centimeters in front of the mirror. What is the focal length? Well, there's not too much to that one. The focal length, we just did that one. Object is, oh, uh, this requires the our formula. So we have 1 over d naught plus 1 over di is equal to 1 over the focal length. Okay, so we need to lean on that formula to figure out the focal length. Okay, so let's do the math on that one real quick. I was thinking about another problem. I'll just write it in between here. So let's see. An object is 12 centimeters in front of the concave mirror. So that's the distance from the mirror to the object. So 1 over 12. So d naught is the distance of the object. The image is 3 centimeters in front of the mirror, plus 1 over 3 is equal to 1 over f. So very similar to what we did with resistors that are in parallel. We should be able to figure out f. So we'll do the math on this part right here. That becomes, what's that, 4/12. So this is 4/12. So 5/12 is equal to 1 over f. So f should be equal to 12 over 5. What's that, 2.4? The units were in centimeters. You don't necessarily need to convert to meters. So the focal length should be at 2.4 centimeters. Okay, so that's probably a good formula to have written down and to know, how that all works. So d naught is the distance to the object. Di is the distance to the image. Number 21, I will ask you to draw a ray diagram. So again, make sure that you have some straight edge, something to draw a really nice, clean, sharp image. Nothing hand drawn like I'm drawing here, right? So I'm looking for, the only thing that probably should be a little bit off base, maybe your semicircles. I get that, but your straight edges, I can draw straight lines on here, should be straight, okay? And they should be to scale. So for example, with number 21, it says you're gonna submit a ray diagram of an object that's 20 centimeters in front of a concave mirror. So if you can fit 20 centimeters on it, go for it. I think you should be able to. If you're not sure, you can scale it back. So maybe, or if you want to scale it up, you can. So maybe, I don't know, 1 inch. I'm just trying to think in my head how would you scale it, but I think 20 centimeters is reasonable on your screen. But if this one is 20 centimeters, this should be, a little bit more than half of this 20 centimeters. So if this is your 20 centimeter mark, a little bit more than half would get you about right here for 12.5. That's what I mean to scale, okay? And obviously 10 centimeters would be here. And you should be able to create your array diagram based off of that. All right, number 22. It says to name the schematics. We've gone through all of these over the semester. The only one that looks a little bit different is this second one that is a battery. So you have a battery, a resistor. They're all set up in that same order. You have a capacitor. And you should know that what they are also by just the units associated with them. So we have ohms here. You have, sorry, I went cover that up, but that's in volts. Capacitors are in farads. Inductors are in henries. And a switch doesn't have any units, but it controls current flow. Okay. So before I sign off on this, does anybody have any questions? Okay. Let me just go back to the other document. Yeah, it's giving me some issues in here. Let me downloaded it, but let's see. Anyway, that document, I'm going into Canvas again. I think what we just went through is a little bit more robust and covers more information. I'm going in, I know I'm not sharing my screen, so I'm going into the modules area. We went over the one that has LOL PDF at the end. I'm gonna pull up this other one. I don't want to download it. I'm having issues with downloads. So I'll share my screen with you. Should be sharing, I believe. Can somebody unmute their mics and let me know if you can see my screen?
No.
Yeah, we can't see
Yes. Okay. So, for sake of not downloading this and putting it on my Notability app, you can see that most of these problems that we just went through are the
Yes, sir.
same. Yep.
Oh, we can't see it.
You can't see it?
Yeah, we can.
Okay. Thank you. There we go. Okay, so you should be able to see that.
Yeah, now we can.
Okay, thanks. All right. And you can see here from this, which if, again, I apologize if some of you guys went through this. I think we went through pretty much all of the same problems, but what I did was I cleaned them up. So like this number 6 is more for my face-to-face class, and number 7, so I wouldn't worry about the actual physical structure for you guys. When you're in industry, you'll see ammeters and voltmeters and decade boxes that are of multiple looks and feels, so I wouldn't worry too much about that. We talked about how an ammeter and a voltmeter are connected. We went over number 10, number 11. I wouldn't worry about number 12. That's called a vernier scale. We weren't able to do anything with that. 13, 14, 15, we went over 16, 17 as well. I wouldn't worry about determining nearsightedness for diverging lenses. 18 and 19 and 20. Yeah, this semester so 22. So I think all of those problems are, we covered pretty much that are applicable for your final exam. Okay. So if you went over this this part of it, you should be just fine. We covered everything that I think is applicable for you guys for your exam. So in the meantime, what I would do if I were you is I would look over those lab reports that you submitted. I know some of them are still pending. Hopefully, you guys have um, some uh, some copies of the ones that have not been graded, so or even have been graded. So if you are the person that holds that copy, please share it. Or if you guys have it housed somewhere, please look it over. If you have any specific questions about, how what you're supposed to get out of it, because I may not be able to get it all back to you before the second or whenever you take your test. Please set up a meeting with me so we can discuss those components. But I think I covered everything. I'll put a note also, send you guys an email about what you're supposed to be doing in the interim between now and the second. And that is it. So make sure you have your cameras, your note cards, your straight edges, everything ready in a couple weeks when you come off of Thanksgiving break. All right. Does anybody have any last minute questions?